Hello and welcome to our lesson on linear functions and graphing. So in our previous topic, we talked about the coordinate plane and how to plot points as locations on the coordinate plane. Now we were just looking at random coordinates, but typically we have coordinates that come from functions and we put them together to make graphs for those functions. So we're going to be focusing on linear functions in this particular section, but first I want to talk about just what it means to be a function. And we're going to get more into this definition later, but for now, in general, a function is an equation. So you're still going to see an equal sign, and in that equation, instead of just one variable to solve for, you're looking for two variables. So a function is an equation that relates two variables, and usually we use the variables x and y for our function. Now, again, there's a little more to the definition of a function, which we will talk about later, but for now, we're trying to identify a function as an equation containing two variables, usually x and y. And the relationship between those two variables is something that we can illustrate on a graph. Okay, we can illustrate that on a graph, which we can also call our fancy coordinate plane. Okay, now just for a second here, let me make sure we're good on some vocabulary. So if I was looking at an expression, I might have something like 3x plus 1. This is an expression, and generally what we try to do with expressions is simplify, although there's nothing I could do to simplify this particular expression. Unless I put, let's say I put a 2 here, then I could simplify this expression and make it a 6x plus 2. Now, if I'm looking at an equation in which we're trying to solve for one variable, then maybe we have something like 6x plus 2 equal to, let's say, 8. Then we could solve that equation for the one variable. So expressions we try to simplify, equations that contain one variable we try to solve, and now what we're adding into the mix here is the concept of a function. So a function is still an equation. It's got an equal sign, unlike the expression, which does not contain an equal sign. So a function still has an equal sign, but instead of one variable to solve for, you might have something like 6x plus 2 equal to y. And so instead of solving for one variable in your equation, then this relationship between two variables in the function is something that we can graph. Okay? So for expressions, we have no equal sign and we try to simplify. For equations, with one variable, we're looking for that equal sign and we're trying to solve. Now a function is still an equation, but because it has two variables, we graph the relationship between those two variables. Okay? So back to the notes. Again, we're trying to illustrate the relationship between a function on a graph or a coordinate plane. And what we're going to look at here are what we call linear functions. And graphs that are formed by linear functions, if you can imagine, they're straight lines. And the equations of linear functions all have something in common. What you're going to see in a linear function, which again, it's just an equation that's going to have an x and a y in it, but specifically we want the x and the y to be to the first power. So x to the first and y to the first. So for example, if you had y and then you had equal to an x squared, that higher power there means this is no longer a linear function. So what you're looking for is x and y to the first power. So x and y to the first power, exponents of 1. Okay? And again, that's something we're going to talk more about later. But there are three common forms that we see for linear functions. One of them we call slope-intercept form. So slope-intercept form is y equals mx plus b. In fact, that may look familiar to you, but notice we have our equal sign to make this an equation. We have, and that highlighter is gigantic, we have our equal sign to make this an equation. We have our y to the first and our x to the first. So that's what makes this a linear function, where the m and the b get replaced by other numbers. So this is just the formula version of our slope-intercept form. An example of an actual linear function in slope-intercept form might be something like y equals 3x plus 1, where the m and b again are replaced by numbers, but we still have our equal sign in there, and we still have our x to the first, and we still have our y to the first. All right, then we have something called standard form. Similarly, we are going to leave our equal sign, our x to the first and our y to the first, but a, b, and c get replaced by numbers. So that is the formula for standard form. An example of a linear function in standard form might be something like 8x plus 3y equal to 12, where a, b, and c get replaced with numbers, but again, you still have your equal sign, you still have your x to the first, you still have your y to the first. And then the last one, which again, these aren't the only three forms, but these are the common forms, is y minus y1 equals m times x minus x1. This one we call point slope, where y, equal sign, x are going to stay. The rest of it gets replaced by numbers. So that's your formula. An actual example might be something like y minus 4 equals 3 times x minus 5. And I'm just making these numbers up. Okay? So these are actual examples of how they might look when those formulas are the variables in our formulas are replaced. But again, notice all of them have an x to the first, y to the first, and that equal sign. Okay, so before we get to graphing, which is the goal, to put some points on a coordinate plane, let's talk about solutions to linear functions. Since a linear function is an equation, just like equations contain solutions, our functions contain solutions. In fact, our functions contain an infinite number of solutions. Now, they are distinct, but there's an infinite number of solutions for every linear function. That means I can make as many as humanly possible and then keep making more, okay? So the difference here is when you're solving an equation that contains one variable, your solution is for that variable only. If you have a linear function, you have two variables, and therefore your solution has to have a value for each of those variables. So each solution will contain a value for x and y, and that solution is going to represent a coordinate, a point on the graph of that function. So again, each of those infinite solutions that are going to be possible contain a solution for x and for y, and we write them as a coordinate. And all of those coordinates are going to come together to make the graph for that linear function. Also, because it is a solution, if we plug it back into our function, it will make a true statement. So each solution will result in a true statement when it's plugged into our function. So let's just see if we can identify whether or not we have a solution if it's given to us. So here's a linear function. We've got x to the first, y to the first, and equal sign. And this one is in standard form if you don't see it, ax plus by equals c. But regardless, is 2, 3 a solution? So remember, in our ordered pair, in our coordinate, in our point, the first number represents an x value and the second number represents a y value. So if this is a solution, we should be able to plug 2 in for x, plug 3 in for y, and end up with a true statement. So 5 is being multiplied by x, but we're going to replace that with 2. Minus y is going to get replaced with 3, and the question is, does that equal 7? Well, 5 times 2 is 10, and if I take 3 away, then yes, 7 equals 7. So that is a true statement that results from plugging in the 2 and the 3, which means, yes, that 2, 3 is a solution. Okay, let's try that again. Is the ordered pair for negative 27 a solution for the same linear function? This time we're going to replace x with negative 4 and y with negative 27. So 5 times instead of x, negative 4, minus instead of y, we're putting in negative 27. Does that equal 7? And notice when I'm plugging in, I'm using parentheses, that way I don't miss any signs. So 5 times negative 4 first becomes a negative 20, and then double negative here is going to make that a positive 27. And when we put together a negative 20 and a positive 27, we get 7. And yeah, 7 does equal 7. So again, this is a true statement, which says yes, that negative 4, negative 27 is a solution. Remember, there are an infinite number of solutions. So let's try this one. If I replace x with 3 and y with -8, do we get a solution? So 5 times -3 minus y, which is a -8, does that equal 7? Well, 5 times 3 is 15. The double negative here is going to make a positive 8. But when I put together 15 and 8, I get 23. And 23 does not equal 7. Does not equal, so I'm going to put a slash through that equal sign. That's the symbol now for does not equal. So since 23 equals 7 is a false statement, this is false. 23 does not equal 7. That tells us that 3 negative 8 is not a solution. So again, our function is going to have an infinite number of solutions, but they are distinct, meaning you can't just plug in any point and it's going to work. So there are an infinite number of points that will work, but not just any random connection of points. Okay? So we can identify solutions if they're given to us. The ultimate goal, though, is to be able to find solutions so that we can actually produce the graph for a linear function. So how do we actually find a solution? If it isn't given to us, how do we figure out where the solutions are? So if we're going to try to graph a linear function by hand, we have to have at least 2 points, right? If I want to graph a line, so a line's going to look something like this, for example, I would have to know at least 2 points. If I can plot 2 points, I can connect those 2 points to make a line. So I have to have at least 2 points on my line to make a graph. So to graph a linear function by hand, you need at least 2 coordinates. And remember, the coordinates are just solutions. So how do we find a solution? Well, because they're an infinite number of them, we can pick any value for a variable that we want. So we're going to start off by picking, just pick a value for a variable to plug in. It doesn't matter which variable, it doesn't matter which value you pick, just pick something, start somewhere, and plug it in. And then you have to solve for the remaining variable. So you're picking something for one of the variables, you're plugging it in, and then you're going to solve for what's remaining. So you can pick any variable you want to start, but there will be a specific corresponding value that goes with that. And the resulting x and y is going to represent a point that are on your graph. So you can connect any 2 points, any 2 solutions to create the graph for your linear function. Okay, so let's look at this example. Y equals 2x plus 1. I'm going to pick a value for x. Doesn't matter what you pick, okay? Just pick a variable, pick a value for one of the variables. I'm just going to choose. I'm going to pick x equals 3. Okay, I like 3, so I'm going to choose it. Doesn't matter what variable, it doesn't matter what value, just pick one. So I'm going to pick x equals 3 and I'm going to plug it in. If I plug it in, then I'm going to have y equal to 2 times, instead of x, I'm putting in 3, and then I have plus 1. And see what happens is I can find the value of the remaining variable. So 2 times 3 is 6, and 6 plus 1 is 7. That means when x is 3, the corresponding y value is 7. So that means there is a point on this graph at 3 and 7. So there's 1 point. So I can go ahead and plot that. That point at 3, 7 tells me from the origin to go right 3 and up 7. So there's that point. And now I need a second one so that I can connect them and make my graph. So I am going to pick another value. Now, again, it doesn't matter what you pick. Although I think in this particular case, this is our slope-intercept form, which we'll talk more about later. I think it's easier to pick an x. So for instance, let's say I chose y equals, let's say I chose y equals 4, okay? If I plug the 4 in for y, and I'm left with 2x plus 1, then when I go to solve for x, I have to do a little more work. I actually have to do some solving here. So I would subtract, which would leave me 3, and then I would have to divide by 2, but that's going to give me a fraction, and I don't want to have to graph the fraction. So instead of picking a value for y, which ended up being a little complicated, I'm going to continue to pick a value for x. So let's say I picked x equals, I don't know, let's say we pick x equals 0. That's an easy one to pick. If I plug 0 into my function right there, if I plug it in there for x, I'm going to have y equal to 2 times, instead of x, I'm putting in 0, and then plus 1. Well, 2 times 0 is just 0, and 0 plus 1 is 1. So when x is 0, the corresponding y value is 1. That means there is a point on my graph at 0, 1. So don't move left or right, just go up 1 to make that second point. Now I can connect and make my graph. So I'm going to use my straight edge, which is a nice little tool here. Try to connect these. Geez, okay, easier said than done. That's pretty good. And we want to, even though those are the only 2 points that I picked, technically I could pick any value of x, plug it in, get its corresponding y value. And so we want to make sure that when we draw our line, that we extend it beyond the points that we've picked, and then we put the little arrows to say this is going to go forever in both directions. And recognize that every single point on this line, every point on this line is a solution. Every point on the line is a solution. I just picked 2 of them to make the line, but all of those points are solutions. Okay, and again, there's an infinite number of them. All right, let's try that again, but this time I want to organize the work a little bit differently. So you've probably seen this before, but we can make a table of values to try to organize the work, where again, we're just going to pick something for x, like let's say we plug 2 in for x, and we're going to find the corresponding y value and just write it in the table, where each x and y represents a point on our graph. So we can organize this information into a table. It might make it a little easier for you to follow what we're doing. So again, I'm just going to pick 2 for x, and if I plug that into my function, again, I'm going to plug it in right here for x. So I'm going to be looking at y equal to negative 3 times, instead of x, I'm going to put in 2 minus 5. Well, negative 3 times 2 is negative 6, and negative 6 minus 5 is negative 11. So when x equals 2, y equals negative 11. So again, this represents a point on my graph at 2 and negative 11. And I did not make my graph go that far. Goodness, I should have picked something a little more strategic, but let's see. I could probably fit it in. So 2, negative 11, that means go right 2 and down 11. Oh yeah, that's right. It's right there. Right on the edge of my graph. Okay? So now let me pick, we pick whatever we want, but 0 is a nice one. I like plugging in 0. If I plug 0 in, negative 3 times 0 minus 5. 0 is nice because it makes that part go away, right? Anything multiplied by 0 is 0. So we just have 0 minus 5, which is a negative 5. So when x is 0, y is negative 5. Again, this represents a point on my graph at 0 and negative 5. And now I can connect these to make my line. So I'm going to connect. Oops. I'm going to actually try to go through the points. Nope, terrible. Hey, that was not too bad. Okay. So there it is. Again, just make sure you're extending beyond the 2 points that you picked, because there is an infinite connection of those that will go on forever. All right, let's try again here. Got a fraction. I don't know if that makes any of you nervous. So I'm going to organize my work into a table. I'm just going to pick some values for x, plug them in, figure out what's left for y. So when I pick a value for x here, again, 0 is nice. I'm going to plug 0 in. So y is going to equal 1/2 times 0 goes in there for x plus 7. Well, 1/2 of 0 is 0, and 0 plus 7 is just 7. So 0, 7 is 1 point on my graph. So don't go left or right, just go up 7 to make that first point. And then the second one I pick, again, I want to be a little strategic. I can pick whatever I want for x, but I don't know if I want to put an odd number in there, because taking half of an odd number isn't going to work so nicely. So I'm going to pick a nice even number like 4. If I plug 4 in, half of 4 I can do, right? Half of 4 is going to be 2, and when I add that to 7, I get 9. So 4, 9 is going to be another point on my graph. So I'm going to go right 4, up 9, make another point, and now I can connect these to make my picture. So connect. That was, darn, I think that was my best one yet. Alright, so there it is. And we got one more. Now this last one is not in the same form. It's not in slope-intercept form, but we can still do the same thing. So let's make a table of values. And this time I don't think it matters which variable we pick. Since both of them are on the same side of the equation, it's going to require the same amount of work, regardless of what variable we plug in. So let's stick to our trend here. Let's say we put 0 in for x. That's going to give me 2 times 0 plus 3 times y equal to 6. Well, 2 times 0 is 0, so I'm just left with 3y equal to 6, which means to solve I would have to divide both sides by 3, and that means that the y value has to be 2. So y equals 2 when x equals 0, so there's 1. Now the second one, you saw how nicely it was for the 0 to go in there for x. Maybe we want a 0 to go in there for y. It doesn't really matter what variable we pick. It wasn't so convenient in the other examples. This time I'm going to start by putting a 0 in for y. And so I'm going to have 2x plus 3 times 0 goes in there for y equal to 6. Well, this time 3 times 0 cancels out, so I'm just left with 2x equal to 6. And so if I divide both sides by 2, then I can see x has to be equal to 3. So 3, 0 there. All right, so my first coordinate was at 0, 2. So don't go left or right, just go up 2. And then my second coordinate is at 3, 0. So just go to the right 3. And there's that. Now I have 2 points that I can connect to make my graph. Oh, I missed. Okay, good enough. Good enough. There it is. Okay? So you're just making solutions by picking a value for a variable, plugging it in, and seeing what's left for the other variable. Sometimes it requires some solving, sometimes it doesn't. Just kind of depends on the form. But plugging in zeros are always kind of nice. And here's the really great news. Okay? We did all this graphing by hand, but we do have technology that will graph for us. And so if we want to verify our work, we go to our handy-dandy calculator, our free graphing calculator called Desmos. So let's look at the first one. And we have y equal to 2x plus 1. Let's see if our graph looks like that, and it does. So that's good confirmation there. And let's put in the next one, which was y equals negative 3x minus 5. And let's see, does our graph look like that one? Sure does. Look, I can see that it's crossing at that point 0, negative 5, so that looks good. And let's look at the third one. The third one we have y equal to 1 half, and then an x, and then a plus 7. And that one looks a little flatter, and yep, matches up pretty well with what we did there. And again, I could see it touching the y-axis at 7, just like my point there. And then the last one, again, just so we can confirm, we've got 2x plus 3y equal to 6. And it looks exactly like my graph. I got a point at 0, 2, I got a point at 3, 0, so everything is confirmed, okay? So we should be able to find solutions by hand and use them to produce a graph by hand, but fortunately for us, we have technology that will confirm everything we're doing. All right, so I think you have enough to go on for your practice assignment, but as always, if you need some extra help, then just reach out. All right, take care.